Chapter 3, we introduce two main methods of analysis, nodal analysis and mesh analysis. And this video will cover mesh analysis. A separate video has been produced covering nodal analysis. So mesh analysis is a good procedure to apply Kirchhoff's laws at various points in the circuit. Particularly, we are looking at using Kirchhoff's voltage law to find unknown currents. And so, before we get into talking about mesh analysis, it's important that we remember what a mesh is compared to a loop. So a loop is any closed loop path that doesn't have any node pass through more than once, while a mesh happens to be a loop that does not contain any other loop within it. So this may manifest itself as a large loop around an outside of a circuit, but if you can't pass through any other loop within a particular loop, then it is a mesh. So we'll see some examples of that as we go forward. In order for mesh analysis to work, the circuit being analyzed has to be planar, and that means if you can draw the circuit such that all of the components are in a single plane, that is a planar circuit. But if you have a component that is connected in such a way that it would always cross over another branch, then that is not a planar circuit. So some examples here. On the left-hand side, this is a non-planar circuit. Why? Because the branch right here in the middle with the 13 ohm resistor going from this corner to this corner cannot be drawn without crossing over another branch in the circuit. There's no way to stretch that out without that particular branch crossing another branch in the circuit. Whereas over here on the right, as this is drawn, we see that this branch is crossing over another branch right here, and this is crossing over. But if we were to stretch this out, the 5 ohm and the 6 ohm here, now this is a planar representation of the same circuit, and we can do mesh analysis with a circuit that is drawn this particular way. So what are the steps in mesh analysis? Number one, you want to assign a current value to each of the meshes. So you're not going to assign and say, well, this is 5 amps, this is 7 amps, but we'll just call those variables. So each mesh will have its own mesh current, I1, I2, all the way up through N for each of the N meshes. Then you're going to apply Kirchhoff's voltage law to each of those meshes, and recall that Kirchhoff's voltage law says if you start at one node and go all the way around from that node back to itself around the mesh, then you're going to see no net gain in potential. And so we're going to see voltage rises and voltage falls, but the net result will be zero gain in potential, and that will allow us to formulate our equations that we can use to solve. We will develop n simultaneous equations to find the n mesh currents, and so we're going to solve those resulting n equations. So let's look at an example here. We do have two different meshes. We see here that we have the mesh on the right, which goes A, B, E, F, and then back to A. And then we have the mesh on the right, B, C, D, E, and back to B. The outside, this loop A, B, C, D, E, F, A, is a loop but is not a mesh because this loop contains the left and right mesh that you see there. And so our first step is assigning mesh currents to each of those meshes. And you can see we've assigned a mesh current I1 over here to the left mesh and a mesh current I2 over here to the right mesh. In this particular example, we just have voltage sources. So voltage sources are a very easy component to analyze as we go through Kirchhoff's voltage law. Once we introduce current sources, and we'll see an example of that a little bit later, there's a couple different tricky rules, just like when you have voltage sources and you're trying to do nodal analysis. So in this case, we just have voltage sources, so that makes it nice and easy. So now what we're going to do is apply Kirchhoff's voltage law to each of the meshes. Let's start with the mesh on the left. And we see if we start down here at the bottom node F, we're going to come up through this voltage source, so we'll see a negative V1. So when we go through voltage sources, if we hit them from the negative terminal, we're going to say that's a minus. And then if we're going in the direction of the current of the mesh around the loop through a resistor, we're going to add that equivalent voltage drop. And so Ohm's law tells us that the voltage dropped across this resistor is R1 times I1. And so we're going to add R1 times I1. And then if we come down through this mesh, this is interesting because right here in the branch where R3 is, that actually belongs to both meshes, the I1 mesh and the I2 mesh. And so in this case, we're going to say we have a current I3, which is really I1 minus I2. So if you look at how the mesh currents interact, they have a resultant vector, which you can think about as being the sum of I1 going in the direction, and the difference being minus I2 going in the opposite direction. So you have I1 minus I2 times R3. And then we get down here and we're back to F where we started. And again, we can't have any gain in potential going around and back to the same node. So that is our complete equation. Then over here on the right mesh, we can start up here at the top at node B, and we're going to have R2 times mesh current I2. Then we're going to have plus V2, because as we go around clockwise here, we're going to hit the positive terminal first. And then if we get back here, we're going to have plus R3, and in this case now, I2 is in line with that, and then I1 is opposing it as we are going around clockwise. So I2 is in the direction, I1 is in opposition. So that's how we have positive I2 minus I1. Now what we're going to do is get our coefficients into the coefficients for I1 and the coefficients for I2 in each case, and our voltages are going to be constants over there. So in this case, if we take this equation for the left mesh and we just want to group together our coefficients for I1, we see we have an R1 times I1 and an R3 times I1, so we'll have the coefficient R1 plus R3 times I1. And then gathering together, if we just distribute this R3 and then negative I2, we have negative R3 times I2, and then this voltage will just move over to the other side. That will be a constant. And we'll do the same exact thing with our right mesh equations. So now what we have are two equations, and normally we would know those resistor values and we would know the voltages of the voltage sources. So if we had that, the only unknowns that we would have would be the currents I1 and I2, and we would have two equations, two unknowns, and be able to simply solve that. Now, what do we do if we have mesh analysis and we have a current source involved? Well, this case here, if you see this particular circuit, has a current source that is only in one of the meshes. So the 5 amp current source over here on the right is only part of the right mesh. And so in that case, that becomes very easy because that tells us exactly what that corresponding mesh current happens to be. So the 5 amps is actually pointing in the opposite direction of the clockwise notation of I2. So what that tells us is that I2 is going to be equal to negative 5 amps. If they were pointing in the same direction, you would have a positive 5 amps. So if we had flipped the current source around and had it pointing downward, that would be in the direction of I2, and I2 would be positive 5. Because it's in opposition, then I2 is negative 5 amps. And all that means is we don't have to do Kirchhoff's voltage law around the right mesh, and the only mesh in this equation we would have to analyze with that would be the left mesh. So we would still get our equation the same way that we would do it before, but now we just simply know that I2 is equal to negative 5 amps. That's the easy opportunity to have a current source in there. We also may run into some challenges if the current source is shared between two meshes, and that will require us to use a super mesh. So in nodal analysis, if you remember and have gone through that video, if you happen to have a voltage source that is between two of your non-reference nodes, then in that case you had to do a super node, really encompassing the equations at two different nodes. If you had a voltage source that was just between the reference or ground node and any other point, then that told you exactly what that node voltage was. And the same is the case for current sources here in mesh analysis. And so if you have a current source that is not exclusive to one of the meshes, if it's shared between two of them, then what you need to do is encapsulate the two corresponding meshes and combine them into a super mesh. So let's see an example of that. Alright, now with a super mesh, that is going to be a little bit different because it's also going to involve Kirchhoff's voltage law as well as Kirchhoff's current law. So we're going to see a constraint equation formed along with the super mesh equation. So when you combine two meshes and only get one equation out of those two meshes, you need to still have n equations to solve for the n unknown mesh currents. And so the last equation is going to come through Kirchhoff's current law. So we'll see an example of that in just a moment. So let's suppose we had this circuit here, and notice that we have this 6 amp current source, and it is going to be shared between the I1 mesh over here and the I2 mesh over there. So what we're going to do is basically ignore the branch in the middle, and we're going to treat this larger loop as though it's one big mesh. Now we're still going to have individual mesh currents through the appropriate components. What that means is over here, I1 is what's flowing through the 6 ohm resistor and the 20 volt voltage source, and I2 is what is flowing through the 10 ohm resistor and the 4 ohm source. So don't be deceived and just think, well, now that we've pulled out that middle branch, everything is in series. We're just ignoring the fact that there's a middle branch. That doesn't mean that I1 in fact equals I2. We're not saying that around that loop we have the same exact current. So we're going to express I1 where it's appropriate, and then over here express I2. So in this case, what we're going to do is ignore the 2 ohm resistor and ignore this particular 6 amp current source for right now. And so if we go through and apply Kirchhoff's voltage law around the super mesh, if we start here at the bottom left corner, we get negative 20 volts plus 6 ohms times I1 plus 10 ohms times I2 plus 4 ohms times I2. That equals 0 because now we're back at where we started at this bottom. And then if we condense our I1 terms and our I2 terms together, we get 6I1 plus 14I2, and then we can move the negative 20 over to the right hand side. So we just get 6I1 plus 14I2. So what is our constraint here? Well, what you can see is this 6 amp source is in the same direction as I2, and it's in opposition to I1. So what you could say is I2 minus I1 equals 6 amps, or you could write that as I2 equals I1 plus 6. And so that is going to be our constraint equation, which will allow us to still have n equations for n unknowns. In this case, our n is 2. We have 2 meshes, and we get 2 equations. This being the first from the super mesh, and this being the constraint of the super mesh currents. This comes from Kirchhoff's current law, which tells us that the sum of the currents has to equal 0 at any given point. So if we were to do the sum of the currents right down here at this node at the bottom, we would see we have I2 coming in, I1 leaving, and 6 amps leaving. And so in this case, our I2, which is the only current coming into that node, has to be balanced with the 6 amps and the I1 leaving. So that is our constraint equation that comes from Kirchhoff's current law. So if you were to take those 2 equations and use any of the techniques that you've hopefully learned in a linear algebra class or some other course where you solve simultaneous linear equations, you could determine that I1 is equal to negative 3.2 amps and I2 is equal to 2.8 amps. What does a negative current mean? All that means is if we drew the arrow clockwise, the current in that mesh in fact actually just goes counterclockwise. So just like if you solved for a vector in a statics course, if you get a negative value, that just means you drew the arrow in the wrong direction. And the math fleshes that all out and allows us to see what the true current is and the true direction of that current. So you could solve these in MATLAB, or you could solve them just by hand. You could just take everywhere you see an I2 in this, you could sub in an I1 plus 6 and then just solve for I1 and then plug that back in and get I2. There's various algebra techniques that you could do with two variables, two unknowns. Once you get to multiple meshes, MATLAB will be highly recommended, and I'll show you guys how to do that in class. So note we're using both Kirchhoff's voltage and Kirchhoff's current law to solve this problem. So you might ask yourself, how do I choose whether I'm going to use nodal analysis or I'm going to do mesh analysis? Well, in some cases, one is going to be more efficient than the other. You might have a circuit that has a whole lot of nodes but doesn't have as many meshes. And so in that case, realize that for every non-reference node, you're going to have an equation. And if you have a bunch of meshes, for every mesh, you're going to have an equation. You might also think about, are you asked to find a voltage or are you asked to find a current? If you're asked to find a voltage, then nodal analysis may be the way to go. If you're asked to find a current, then mesh analysis may be the way to go, because that's what you natively get out. Of course, you can easily go back and forth between those, because if you use Ohm's law, if you know current and you know one of the resistors, you can easily find a voltage drop. If likewise you know a voltage at two different nodes and you want to know the current that passes from one node to the other through the particular elements between them, then you can easily just apply Ohm's law and look at the difference in voltage divided by the resistance between them and figure out that particular branch current. So if you think about the information that's required, if you think about the particular network of resistors, that helps you figure out which approach is best. So in general, I would recommend using mesh analysis if the network has a lot of series connected elements, if it has voltage sources, and if it has super meshes, or if it has fewer meshes than nodes. If branch or mesh currents are what you're looking for, then that's when you want to use mesh analysis. If you're asked to find a current through a particular resistor, mesh analysis will give you that directly, or can easily be found just by finding a difference between two mesh currents. And it's the only suitable analysis if you have transistor circuits. And so we're not going to do a whole lot of solving of transistor circuits, but just keep that in mind that nodal analysis doesn't apply. It's primarily based upon currents going in different directions, and so mesh analysis is going to be the only analytical technique for transistor-based circuits. This is not going to be appropriate once we start getting into operational amplifiers, largely because obtaining the voltage across an amp is particularly difficult. So once we get into op amps in Chapter 5, we're going to hone in on some analysis techniques, primarily using nodal analysis in that case. You want to use nodal analysis if you have a lot of parallel connected elements. So in that case, when things are in parallel, you have the same nodes shared between those elements, and that allows you to reduce the number of equations. Whereas if you try to do mesh and you had, let's say, 10 resistors all in parallel, even though they share the same voltage across them, you're going to have several different meshes that you're going to have to analyze, and that's going to make it a lot more challenging. If you happen to have current sources, nodal analysis makes it really easy. And of course, if you have supernodes, that is, if you have a voltage source that's shared or happens to be between two different non-reference nodes, then that really makes it a lot easier to do nodal analysis with rather than our mesh analysis. And so in general, if you have fewer nodes than meshes, that's the technique that you want. And if you have non-planar circuits, you can use nodal analysis. Mesh is off the table, but you can use nodal analysis in that case. And oftentimes nodal analysis is easier to solve by computer, but we can do nodal and mesh in MATLAB with our modern computational tools. So that's no real big deal. So this concludes our discussion of mesh analysis, and I'll be preparing some other videos with some examples of how to solve some of these problems.